Hello everyone, in this video I just want to talk about how to draw out the chair conformation and flip the ring, and also we are going to just look at how you can convert a bound line drawing to the chair and also to a Newman projection. Okay, so let's get started. First of all, chair conformation is for the 6-membered ring that all these items on this ring, they are sp3s. So most of the time, if we are looking at cyclohexane, that's our carbons. So all those carbons is sp3 carbons. And cyclohexane is like this. And we already know that they are not flat, right? Because the sp3 carbon, they are tetrahedral structure. And for cyclohexane, the most stable conformation is so-called chair conformation, and we can draw it out, chair conformation. And the reason why chair conformation is the most stable is because it has no angle strain, perfect tetrahedral for the carbons, and no torsional strain, because all the group connected to these carbons, they are staggered. We know that staggered in Newman projection, staggered conformation give you no torsional strain, that give you the most stable conformation, and that will apply here as well. That's why chair conformation for cyclohexane or the 6-member ring with sp3 items will give you the most stable conformation. And go to draw out the chair conformation, because what we draw out is what we see is look like a lightning bolt. I usually just draw it like a lightning bolt. So what we are looking at here is these two bonds right here, okay? It's parallel, and then these two blue ones, they are parallel. These two green ones, they are parallel to each other. And then on the chair conformation, if it's just simple cyclohexane, we'll have those hydrogens, and if not hydrogen, it will connect to other items or the groups, and we'll have 4 bonds on the carbon no matter how. So the first type is this kind of straight up or straight down ones that are called axial position. And you notice that all these 3 carbons right here, these 3, 1, 2, these 3 carbons, they're kind of pointing up, right? They're kind of going up. If what that means is if you are drawing a line, let's see, just imaginary, there is a line, okay, right here, okay, just draw it a line. All those carbons I just point out, let's just highlight it with purple. And this one, the purple ones, right, they're kind of below, above that plane, and then these 3 yellow ones, they kind of pointing downward. So 3 pointing up carbons, 3 pointing down carbons, and on 3 pointing up carbons, axial position is pointing straight up, straight down carbon pointing straight down. And also you will have, let's see what color we should use here is let's just choose something different. Okay. On the each carbon, because it forms 4 bonds, the other bond will go to sideways. So sideways. The sideways, how we can draw this out? Imagine this carbon right here is a tetrahedral structure. If I draw a little line, okay, tetrahedral, right? You have the pyramid right here. Kind of tetrahedral structure. So imagine, so that's why that kind of brownish colored bond is pointing that way. But it's pointing down, okay. What does that mean? Okay, if you draw a line right here, that this bond right here is below the line, okay. And then for all these pointing up carbons, it will have the bond pointing kind of down. And then for the pointing down carbons, you will have a run out of color. Okay, let's see. Something look like this. Okay. it will have kind of pointing up. Oh, that color did not work. Pointing up groups. Okay, pointing up groups, and draw it here. Okay, some students ask if you can draw this way. It's also okay, it's just fine. So what we are seeing here is this is a tetrahedral, and that is how we draw out the chair conformation. And all this pointing sideways, this brownish, yellowish kind of bound, those positions are called equatorial position. Okay, so now on chair conformation, we know there are axial position pointing up, straight up and down, and pointing on the sideways, side up or side downs is equatorial position. And then the next is we are going to flip the ring. That is the second skill that we have practiced in the class. So just to give you one example, if we have something look like this, okay, and we have this meso group, and then we have this isopropyl group. Okay, so this is one chair conformation. Now we put a double set arrows. That means it's flipping. Okay, so how to flip the ring? Basically, what we are looking at here is this carbon and this carbon. Okay, I will use as blue. So both carbons right now is pointing up. If you are seeing this, is pointing up carbons, pointing up carbon. These three are the pointing down carbons. So pointing up carbons, when you flip the ring, it will be pointing down. So any pointing down carbons on the new lightning bolt I draw here can be these two carbons. So I'm going to use this corner one as red. Then here you see, right, this goes like, if you throw eyeball right here, basically looking down this molecule, it basically like kind of, this is the red carbon, and then clockwise 1, 2, you will have the blue carbon. So if you throw eyeball right here, okay, that is our red carbon. The clockwise, this will be our blue carbon. So blue carbon now will be pointing down as well, because it was pointing up. Then the next thing is the meso group on the red carbon pointing up, straight up, okay, and it's at axial position. Now it will be on the equatorial position. So axial position, when you flip the ring, it goes to equatorial position, and equatorial position. And if you have equatorial position, it go to the axial position. So to be said, then the isopropyl group was on the equatorial position. Now it's going to a axial position. So that is, we flip the ring. So, and now also what we are seeing here is, if you are looking at this chair conformation, this isopropyl group still can pointing down, right? It's sideways pointing down. It's at the equatorial pointing down, but it's still pointing down. So when you flip, it's still pointing down. It's straight down now. And for the meso group, it's pointing straight up on the axial position. And when you flip, it's still kind of pointing up towards your eyeball, pointing up. It's equatorial position pointing up, but still pointing up. So that is the things we can check when you flip the ring. Okay, that is the skill number 2. Skill number 3, what we want to do is we are trying to convert from bond line or skeletal to chair, and we can convert them back and forth, and also Newman projection. Newman projection, while looking down, carbon-carbon projection, carbon-carbon bond. So for example, if we are looking at this bond line, so we have the meso group here, we have a, let's do a isopropyl group right here. Okay, so how to go from the bond line to chair? This is pretty easy. So what we have is, you have cyclohexane, you will have a chair conformation. And then what we'll do is we'll label this ring. The reason why we label this ring is not for naming, okay? It's for correct carbon at correct position, and also have the correct substituent. So what we will do is, okay, we'll random draw a lightning bolt to the chair conformation right here for the cyclohexane ring. And then for this case, I'm going to label this as 1. So imagine if you are putting an eyeball right here over to look at it. 2 will be this one because this 2 right here is on your right side. If you looking down, it's a clockwise. So 2 and 3 and 4, 5, 6. That is how I see this molecule. From the chair conformation, you put an eyeball there, that matching the numbering that you have for the bond line drawing. And then we are going to put the group onto the chair conformation. So first group is the methyl on the carbon 1. Methyl on the carbon 1. Carbon 1 at this moment is a pointing up carbon, right? Pointing up carbon. It have a methyl group pointing towards your eyeball. In this here, you are standing in front of the paper plane. It's pointing towards you. That means pointing towards your eyeball, right? So that pointing towards your eyeball is a straight axial position methyl group at this moment. And then you have the isoprop group on the carbon 3, and carbon 3 also is pointing up carbon. So it's on a wedge. Then that means this is also, let me change another color. This is also on the axial position. So this is a chair conformation that I draw for this one. And what we can do is, of course, we are going to flip the ring. When you draw the chair conformation, you always flip the ring because the one you draw here may not be the chair conformation that is preferred because they have higher energy. A molecule tend to stay at lower energy possible, so they prefer the lower energy conformation. So we will flip the ring. We are going to flip the ring to draw a backward kind of lightning bolt compared to the original one, and we just labeling. So now the labeling is, because your carbon 1 on this one is pointing up, so any carbon on this lightning bolt I draw that pointing down can be 1. So I will do this as 1 and putting eyeball there, okay? Clockwise counting to numbering. So this will be the number. Okay, and now what we see here is you have a methyl group. I'm going to highlight this methyl group. Methyl group pointing towards your eyeball, and it was on axial, now it's at equatorial position. But if you are looking at, it's still pointing up, right? Still pointing up. It's side up. It's like equatorial side pointing up. And then you have the isopropyl group, right? It's kind of sideways equatorial position, but still pointing up towards your eyeball. So flip the ring, and you will have the chair conformation for this molecule that is shown in bond line. So the next thing is how we can do this in a Newman projection. So the whole idea for Newman projection is that we are going to throw our eyeball sideways to look down the carbon-carbon bond. So for example, if I throw, purple. Okay, purple. If I throw eyeball right here to look down 3 and 4, and throw another eyeball to look down to carbon 1 and 6. So basically what I have here is this is carbon 3, and then you have carbon 4. This is carbon 1, and you have carbon 6. And then you draw what you see, right? What you see here, first of all, this will be the carbon 2, right? And then you will have a side pointing away isopropyl group. I'm going to highlight this here. And then you will have a hydrogen that is not drawn on the chair conformation, but you need to know that there is a hydrogen right there. And for the back, it's just hydrogen, and it's chair conformation, so it's staggered. And in the back carbons, this left circle is carbon 4, and this right circle is carbon 6. They were connected by carbon 5 in the back. Okay, in the back. I should not draw that way. It's not back this way. It's back sideways. Okay, and for the carbon 1, if we are looking at here now, if you imagine yourself throw your eyeball right here, looking that way, you will have this methyl group pointing sideways, and then we'll put in the hydrogen right here, and for the back carbon 6 you have this hydrogen. So this is a Newman projection from what we drew in the chair conformation. You may say, then how do we draw the chair, Newman projection for the first chair conformation while looking? So it depends on which carbon-carbon bond you are looking down, right? So for this one, we're still looking down the carbon 3, carbon 4. Imagine you put the eyeball right here looking down, and then your eyeball right here looking down, okay? So what we see here is 3 and 4, right? 3 and 4. This is 1 and 6. Again, 3 and 1 will be connected by 2. And at this moment, the 2 is pointing down, right? So this is carbon 2. And then for the carbon 3, you have this isopropyl group actually pointing straight up at axial position. And then you will have this hydrogen that is now shown on the chair conformation. And for the back, 4 and 6 connects by 5. 5 is a pointing up carbon, so they will be pointing up this way. And then in the front, carbon 1, now we'll have this methyl group straight up at axial position and fill in the other hydrogens. That will be our Newman projection for the first chair conformation we drew. So what do we see here, basically, right? You see the chair conformation here. You have the methyl and isopropyl straight up, axial position. In Newman projection, they are straight up, right? Straight up. And then these two, they are at equatorial position. They are pointing sideways. Sideways. This is called sideways, right? Sideways. Okay, so that is how you interpret Newman projection and how to convert between the chair, bond line, and Newman projection. For other skills, these are very basic skills, and based on this skill, you know, draw out the chair, you flip it, and then the next step is we are going to look at the energy consideration. So we will talk about that in the class, and this is the end of this video, and it will help you with your homework for this weekend.